Right. We are starting our discussion focusing on waves, sound, and light. So, we shall start by looking at what we call the transverse pulses. Right. In our discussion about transverse pulses, we answer the question about a pulse. What is a pulse? A pulse.
A singular disturbance.
Well done. A pulse is a single disturbance. A pulse is a single disturbance. A pulse is a single disturbance. Okay, so we have that. So now a pulse is a single disturbance. Now, let us look at more notions on these here. There's something we call a transverse pulse. What is a transverse pulse? Right. And also we shall learn about the properties of these pulses and transverse pulses, etc., etc. Okay. Now, there's something that is very, very important here. Okay. Let's look at transverse pulses, but also I want to mention that in a transverse pulse, right, in a transverse pulse, the particles. The particles of the medium. The particles of the medium move at right angles, to the direction of propagation of the pulse through the medium. Through the medium. Okay. Right. So now I want us to focus on transverse pulses for now, but also have a discussion about the properties of these. Okay. So now let us define the following here. A transverse pulse. Right, so a transverse pulse right. So now when we actually first look at the fact that The pulse travels along a medium, but the turns of the medium, for instance, are in vertical positions, up and down, at right angles to direction of propagation. So in a transverse, in the notion of a transverse pulse, the movement of the pulses is such that they move at right angles to direction in which the pulse itself tends to move. And so now this describes the pattern of movement in what you call a pulse, or in particular, a transverse pulse. Now, I want us to have a clear and but very concise discussion about the following features. Okay, so a transverse pulse is a pulse that moves across at right angles. At right angles. Right, so we are defining here what we call a transverse pulse. Obviously, a transverse pulse is a pulse that moves at right angles. Right. At right angles, let's add here, at right angles to the direction of propagation. At right angles to the direction of propagation. Right, so we note that. Okay. All right. Okay, I want to also say a little bit much. That I want you to note that in a transverse pulse, and let's highlight this one. In a transverse pulse, the particles of the medium move at right angles to the direction of propagation of the pulse through the medium. Okay, so that is one thing. So in other words, you can look at a pulse as a single disturbance. The pulse is a single disturbance. But most importantly, in a transverse pulse, the particles of the medium move at right angles to the direction of propagation of the pulse. Okay. So now I want us to sort of have a fair description of this, because if we are really saying in the transverse pulse, the particles of the medium move at right angles to the direction of propagation of the pulse through the medium. Right, so we note that a transverse pulse is in the first place a pulse. And I want to define these differently. I want to involve the word particles here. I want to involve the word particles here in the following manner. Right. Let me clean this up. I want to state this in a more concise manner. So a pulse, once again, is in the first place a pulse. Whose particles Right, is a pulse whose particles, or is a pulse such that, that's better, pulse such that the particles of the medium move at right angles to the direction right of propagation. Is a power such that the particles of the medium move at right angles to the direction of propagation. Propagation of the powers through the medium. Through the medium. Okay, we continue. So now let us look at some properties of a pulse. So it's very important to be in a position to describe the properties of a pulse. So let us look at a slinky spring, right? Something called a slinky. And now, if you look at a slinky, in the rest position, right? A slinky in the rest position would be, if you have the human hand here, and here comes this slinky spring. Like this. Okay, so now this would be the slinky spring in the rest position. This could be the slinky spring, or it is the slinky spring in the rest position. So if this is just a spring that is not stretched, but somebody has just touched both ends of the spring, of the slinky spring. So this slinky spring can be stretched. But now this is the slinky spring in the rest position. Okay, this is the slinky spring in the rest position. Now, if you look carefully, now we can look at the spring just resting. You can consider this spring as resting on a tabletop. Okay, these things here, this is a human. human hand. And this one is also a human hand. It's a human hand. So it's now it's this slick spring is in the rest position and it's rested. Like you can review this as being rested on the surface of a table. If you have a table here, it is on the tabletop. It is on the surface of a table, so on the tabletop. So it is rested on the tabletop. It's resting there and it's sitting. And a person is just holding the ends of this spring. Now let's look at the next thing. Let's look at this spring now. Here is the tabletop still. And then now the spring is like this. Okay, here's a spring. Here is the spring. Okay, now it's like it has gone up in the middle. So because it has gone up in the middle, we're gonna just understand what is happening to the spring here. And okay, now you can have this one here, the human hand. Okay, this one is still the human hand. But also here, this is also the human hand. Okay. Now there's certain things here like your transverse motion of the turns. So this here now, if somebody teases the spring and lifts it up, what is going to happen is he's going to reveal something we call the transverse motion. The transverse motion of the turns. Okay, so it goes it goes that way. Okay, so it goes sort of up and down. So if somebody takes this and teases this and tampers with it, what then happens is it's going to be up and down. Okay, so if somebody like lifts it up at one end, then it's going to go up and then it's going to go down that way. So okay, now it goes up and then it goes down. But what we note, therefore, is because it is moving actually up and down like this, but the direction of propagation is from left to right of the table. and therefore we can see that the direction of propagation, so this one becomes a diagram. So this diagram here diagram of a transverse pulse moving along a slinky spring. Moving a slinky spring. So this diagram here shows the transverse diagram of a transverse pulse moving along a slinky spring. So now in this spring, you can see that if somebody lifts it up like this, it's up and down, up and down, up and down, up and down, and therefore we have that. Okay, let's continue to analyze this notion here. Let us now define a medium. What is a medium? Have you ever heard of a medium before?
Yes.
Okay. I'm excited. I'm happy that you know of a medium, but what do you think a medium is?
The object.
Please come again.
The object.
The object. Well done. It is the object. It is the object. I like that. Let me write it here. It is the object. Well done. So it is a substance through right, a substance through or along which something moves or is transmitted. Okay, a substance through or along which something moves or is transmitted. Right, this is the object. So a substance through or along which something moves or is transmitted is called basically a medium. Right, so now let us look at a couple of definitions here that we need to learn. Let us look at describing a pulse. Describing a pulse. Right, let us describe a pulse. Okay, we've defined a pulse as a single disturbance. A single disturbance is what? Is a pulse. So pulse length. Pulse length. What do we mean by pulse length? Pulse length refers to the distance. The distance from one end of the pulse to the other end. Okay, so by pulse length, we refer to the distance from one end of the pulse to the other end. Okay, so that is pulse length. The distance from one end of the pulse to the other end is called the pulse length. And we're going to show that one. We're going to use a diagram to show this. What is a displacement? There's something we called the disturbance. Right, something called the disturbance or displacement. Okay, so something called the disturbance or the displacement. How far and in what direction a point, right? So now disturbance or displacement, what do we mean by these? And I want to underline these in yellow. Okay. All right, so I'll underline well neatly. I'll underline very neatly. I'll underline neatly. Right. I'll underline neatly. Okay. Okay, good. I'm just getting my pen set up. I'm resetting the pen. That's the reason why I'm doing this. Okay. All right. So now we have the disturbance. Okay, by the disturbance, then at this point, we mean how far and in what direction a point, how far and what direction a point or particle in the medium has moved from the rest position. So now we have disturbance. So disturbance then at this point refers to, or displacement, how far and what direction a point or particle in the medium has moved from the rest position. What do we mean by disturbance or displacement? We refer to how far and in what direction a point or particle in the medium has moved from the rest position. So amplitude. Amplitude. Amplitude, what do we mean by amplitude? Have you ever learned about the amplitude? What do you think the amplitude is?
The height.
The height. Well done. It's the height. I like that. It's the height. So we define the amplitude as a measure of how big a pulse is. Right. So now a measure of how big a pulse is refers to the amplitude. We can mention things like the more energy the particles are given, the further they can move from the rest position. The more energy the particles are given, the further they can move from the rest position. So we are describing here the amplitude. I like your description of the fact that the amplitude itself, you can view it as the height. You can view the amplitude as the height. You can view the amplitude as the height. You can view the amplitude as the height. Okay, so let's continue now. Okay, this is about just describing a pulse, but let's define an amplitude. So we say amplitude is the maximum disturbance of a particle. Okay, so amplitude is the maximum disturbance of a particle from its rest or equilibrium. Or equilibrium. So we continue. Amplitude is the maximum disturbance of a particle from its rest position. Note that here, by the amplitude, we mean the maximum disturbance. Amplitude is the maximum disturbance of a particle from its rest position or equilibrium position. Let's look at a diagram. We shall be looking at some terminology. Okay, some terminology. If you look at this graph like this, and there is this one that goes up this way. And then now, okay, so and these, okay. Okay, so you look at this now, this is called the rest position. It's called the rest position, and there's a vertical displacement. Now, this maximum disturbance from the rest position to the highest point is called the amplitude. This one is called the amplitude. And then, maybe I can even clean this up. So this is called the amplitude. And then now you have this one now that is so now at this point, you need disturbance or displacement. Of particle change in y. Okay, so now let's look at these. Okay. So you can see that there is, if this one is the sort of the wave, this one here, the pulse, right? Here is the pulse. And now if you look at the distance from the equilibrium position or from the rest position, this maximum, the maximum disturbance of a particle from its rest position is the amplitude. So amplitude is the maximum disturbance of a particle from its rest position. So that refers to an amplitude. So it is the maximum disturbance of a particle from its rest position. That's an amplitude. So we have looked at amplitude. We have looked at disturbance. We have looked at the notion of what we call the rest position. If this is the x-axis, there's migration and propagation in that direction. There's propagation vertically. So if this is the kind of the slinky spring that we're looking at, the slinky spring, then you can see the spring now. If somebody tosses it up and pushes it at the beginning, and suddenly you can see the rest of the spring following the motion as shown there. So those are the things that you need to take note of. So as part of these, you must be able to answer a couple of questions. You must be able to answer questions on transverse pulses. Right, so what are these transverse pulses? Let's look at an activity. Right, it is in this activity, what you need to be able to do is to answer questions on transverse pulses. Okay, let's look at number 1. Write down or write definitions for for 1.1 pulse. 1.2 transverse pulse. 1.3 amplitude. Right, amplitude. 2, describe. How to produce. How to produce a transverse pulse using a slinky. Right, using a slinky. We're going to do this activity together now. Number 3, a transverse pulse moves from turn to turn along a slinky. Compare the movement of the turns of the turns with the direction. With the direction that the pulse is moving. The 3.2, explain. What is the title of the textbook that you're using?
Doxentia.
Oh, Doxentia. All right,
Yes.
good. Right, explain how the movement of the turns propagates propagates the pulse. Number 4, you need to draw a graph to show a transverse pulse. In the process, we shall label the axis as well as pulse, length, amplitude, 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 amplitude and rest position. Okay, so now let us write down the definitions of these. Okay, what do you think? Here is an activity. I'm calling it activity 1. Activity 1. Write down definitions for pulse. What do you think a pulse is?
A pulse is a singular disturbance.
Well done. It's a single disturbance. So a pulse is a single disturbance. So look at the solutions here. Good, well done. So one 1.1, a pulse is a single disturbance. One 1.2, and then a transverse pulse. 1.2, a transverse pulse.
A pulse that moves across at right angles to the direction of propagation.
Definitely. Right, so a transverse pulse A transverse pulse is a pulse that moves at right angles to the direction of propagation. Or you can say it's a pulse is, or a transverse pulse is a pulse that moves at right angles to the direction of propagation of the particles. Obviously, if you're looking at the propagation of the pulse, I can write it nice like we wrote before to say a transverse pulse is a pulse that moves, or is a pulse such that, like we said here, a transverse pulse is a pulse such that the particles of the medium move at right angles to the direction of propagation of the pulse. So you can define it like that. There are many ways to state that. But another way to say that is to say, I like this one to say a pulse, a transverse pulse, a pulse that moves such that the particles of the medium such that the particles of the medium move at right angles to the direction, of propagation of the pulse through the medium. Right, so right, let's just analyze this carefully. So we have defined a pulse and also a transverse pulse. So a transverse pulse is a pulse that moves such that the particles of the medium move at right angles to the direction of propagation of the pulse through the medium. Now, this is brilliant stuff. Next, we define an amplitude. What do you think an amplitude is?
It's the maximum disturbance of a wave from its rest position.
Well done. It is the maximum disturbance of the wave from its rest position. That's brilliant stuff. So that's, it can be written in many ways. 1.3. So amplitude is the maximum is the maximum disturbance of a particle from its rest, or right, so we sometimes call that the equilibrium, from its rest or equilibrium position. Just to write this one here. From its rest, or you can say equilibrium position. Right, amplitude is the maximum disturbance of a particle from its rest or equilibrium position. So that is what we have. Right, so we have defined an amplitude. An amplitude is the maximum disturbance of a particle from its rest or equilibrium position. So the couple of things I want us to also discuss here. We need to be able to describe in the second point, describe how, okay? Describe how to produce a transverse pulse using a slinky. Describe how to produce a transverse pulse using a slinky. Now, let's describe this one. Number 2. Right. Right. I want us to just discuss these. Here. So this slinky, let's look at diagram 1. All right, so to describe these, you can use a diagram. Okay, let's have a table here. And okay, let's have the horizontal case first. Now you have the horizontal one. So you can have the, like we saw the human hand, the fingers, and the fingers of the human hand here. Human hand. Then applies this thing here is a table. And this yellow stuff here, yellowish stuff, is the slinky spring. Okay, so now Now let's have more problems. So in the end, here is the table again. This time around, this linky is sort of given some energy and the forces applied to it. It has some kinetic energy. So this one is a hand. It's a hand, and that still remains a slinky. Okay. Now, the couple of things I want us to sort of discuss here. And then we then say, so what happens here is that your hand moves the end turn of the spring sideways. When the end moves, it moves the next turn. So your hand moves the end turn. Of the spring sideways. When the end turn moves, it moves the next turn, which then moves the one next to it. So this is some ripple effect. And we proceed to then say the sideways movement goes along the spring from turn to turn. So now what happens is your hand moves the end turn of the spring sideways. So if you have the spring, then you move it sideways with one hand. When the end turn moves, it moves the next turn. Okay? So because the spring is one object, so when the end turn moves, it moves the next turn. So you move the end, then the next turn moves, and the next turn moves, or the next turn which then moves the one next to it. So it's the ripple effect. The sideways movement goes along the spring from turn to turn. So this sideways movement moves from turn to turn. Moves from turn to turn until such that until such time that there is movement to the other end of the spring. So in other words, the movement begins from one end to the next. And that describes here, it actually describes how to produce a transverse pulse using a slinky. How to produce a transverse pulse using a slinky. Now, the next thing. Okay, a transverse pulse moves from turn to turn along a slinky. A transverse pulse moves from turn to turn along a slinky. Compare the movement of the, that is the one we're discussing now, because we describe how to produce a transverse pulse using a slinky. Right. Compare the movement of the turns with the direction that the pulse is moving. Okay. Compare the movement of the turns with the direction that the pulse is moving. So let's look at 3.1. So the turns, so we can say the movement of the turns is at the movement of the turns is at right angles. Is at right angles to the direction of propagation of the spring. Yeah, or direction of the pulse. Because now compare the movement of the turns with the direction of that the pulse is moving. So you say that the movement of the turns is at right angles to the direction of movement of the pulse. Okay, so now this is what we are effectively saying. So the movement of the turns is at right angles to the direction of movement of the pulse. Right, so the movement of the turns is at right angles to direction of movement of the pulse. Because now what is happening here is the there's up totally, see? Just a sec. Wondering what I did here. All right, so I think I might have deleted something. No mind, I'm going to restore it. So obviously here we're saying a transverse pulse moves from turn to turn along a slinky. Right, you need to compare the movement of the turns with the direction of that the pulse is moving. So in 3.1, once again, I was saying the movement, tool that I think that got deleted. The movement of the turns is at right angles at right angles to the direction of propagation of the pulse. Here we're saying the movement of the turns is at right angles to the direction of propagation of the pulse. I want to have a diagram that illustrates this. So here is a tabletop with legs, and this is a table. So use a different color. So for example, now if you have this, okay, so now here is the slinky spring. Here is a boy that is actually actively on one end here holding the slinky. And also this one is holding the slinky. This one is the hand. This one is also the hand. Okay, and now he's just tossing it, tossing one end up or sideways. Okay, if you toss it sideways, then what happens? We agree that ultimately this spring is such that it is propagating in two effective in a couple of directions first. Let's just mention that. So it goes first because it was moved up. So it first goes up and then down. But ultimately, it will propagate. It's moving from left to right. The pulse has its direction of propagation. So the direction of propagation of the pulse is from left to right. From left to right. Okay, so direction of propagation of the pulse is from left to right. So now, if the direction of propagation of the pulse is from left to right, what then do we say here? So, but it is moving like a snake, you know, like a snake, because now we find that it's just waving like this, but it's going there, but it's waving like this, like waves in the sea. Have you ever seen the sea waves? They go up and down, but the sea is moving towards, the waves are moving towards the seashore. But those waves are actually up and down. Those are the pulses that we see there in the sea. Next question. Three point two. Explain how the movement of the turns propagates the pulse. So here we're to compare the turns and the direction that the pulse is moving. So you can see that it's turning up and down. It's turning, the turns. Those turns are up and down, but the direction is from left to right of this pulse. It's from left to right, but those turns are up and down. Okay, so that's one thing that we note, that those turns are up and down, but the pulse is from left to right. So if you explain how the movement of the turns propagates the pulse. Propagates the pulse. So in other words, let's explain 3.2 now. How the movement of the turns propagates the pulse. How is it that those turns, when it's turning like this, how does it propagate the pulse from left to right? How? Okay, so let's explain that part. We have the notion of momentum as well. So the movement of the turns at right angles. At right angles. Right, so the movement of the turns at right angles to the direction of propagation of the pulse, direction of propagation of the pulse causes the particles in the slinky spring to vibrate, which transfers energy of motion in the slinky which transfers energy of motion in the slinky to propagate from one end to the next of the slinky. Okay, so the movement of the turns at right angle to direction of propagation of the pulse causes the particles in the slinky spring to vibrate, which transfers energy of motion in the slinky to propagate from one end to the next of the slinky spring. Okay, there are many ways to sort of explain this. Of the slinky spring. Okay. So we continue. We continue. Next question. So we're effectively obviously saying that if one teases the spring and gives it an initial move by tossing it up at one end, what it does is this linkage spring will do up and down movements. These up and down movements obviously transfer energy in motion called kinetic energy in the spring, and therefore you find that these vibrates to the end. These vibrates to the end. Next. Right. Here's a question about drawing a graph. Draw a graph. That number 4. Did I put that question here? Yes, draw a graph to show a transverse pulse. Label the axis as well as pulse length, amplitude, and the rest position. We need to draw the graph of a transverse pulse. How does the graph of a transverse pulse look like? We need to draw a graph. There's a graph of a transverse pulse, but how does the graph of a transverse pulse look like? How does the graph of a transverse pulse look like?
There's a line which is the rest position, and then there's a wave on top of the rest position that
Well
shows the.
done. Yes, there's a wave on top of the rest position. I like that. And that's exactly what we're going to draw. Well done. And I'm excited. And congratulations to you for sharing that answer. Is actually a very useful answer. So you have this and you have that. There is some movement in the vertical axis, in the horizontal axis. So, and then you have this kind of a movement. And then now we're going to show if this one here is the rest position. Right, so we have that this one is the rest position. Then it goes up. And this is the amplitude. So, okay, so now this one here is the disturbance. Is the disturbance displacement. Displacement of particle. So that is the disturbance. The disturbance is sort of moving the particles upwards in the delta y, and delta y means the motion in the vertical axis, which is like the y-axis. So there's that disturbance. We have shown the disturbance. And now that is the amplitude, which measures the maximum disturbance. Amplitude measures the maximum disturbance there from the rest position straight up. And then you have the pulse length. Okay, so you have the pulse length. Right, so the pulse length is actually from like here to there, is shown there from the beginning to the end of the pulse, is called the pulse length. So this right, this one here is called the pulse length, which is from the beginning of the pulse to the end of the pulse. So now there's something we call superposition of pulses. So the next thing we're going to discuss now is called the superposition of pulses. Right, superposition of pulses. Okay, now the superposition of pulses becomes extremely important. But first we describe what we call interference. What is interference? Interference is when two or more pulses and waves interact with each other. With each other in the same space. In the same space. The same space and at the same time. Now, so here interference is when two or more. So what we're saying here. It's when two. Right, so interference is when two or more pulses and waves interact with each other in the same space and at the same time. Okay, we're here. We're continuing. What is interference? Interference is when two or more pulses and waves interact with each other in the same space and at the same time. Two or more pulses and waves interact with each other. So we say there's interference because we have two or more pulses there. Two or more pulses. Okay, let us understand these and let's look at a diagram to show this here. Here is the diagram. Here is a diagram. Right, so I'm gonna use another screen because it's okay. Right, gonna use another screen now. Right, so now we're gonna use we're discussing superposition. Right, we're discussing superposition, so get yourself ready. Okay, actually getting to another screen because I want us to continue. All right, getting to another screen for us to continue. Right, we're going on. Right, we're getting to another screen just now. Superposition. Right, so I was speaking about superposition. In particular, we're speaking about interference here. Transverse pulses travel towards each other. From each end of the slinky. So let's look at the human hand. And holding this slinky, and then you have this. So you have this. So here's a slinky now. It's up here, it's up there. It's a bit horizontal here in the middle. And or this one goes up here. Plus 120 millimeters. Plus 80 millimeters. Okay, so there's that upward movement now. This link here is held up, then is pushed up a little bit here, given an upward movement, and suddenly it moves up. But also it moves up here, so there's a pulse and a pulse there, and you can see there's an interference in the. Now they're gonna meet at some point because there's migration. This one is doing up and down movement, and this is also doing up and down movement. But because of this linkage spring that's connected in just one structure, they're beginning to migrate towards each other, one from left to right and the other one from right to left. Right, the disturbances are to the same side. Okay, so we have that. Okay. Now they're there. Like that figure, call this figure 1. And call this figure 2. Right, in figure 2, then you have what is going to happen when these, one of them is 120 millimeters in the height here. The height is that, or the amplitude, and here the amplitude is 80. So let us see what happens. So now you have this one here. Still the hands are there. And now this is the slinky. This is the slinky. Where the two pulses cross, the disturbance increases. So let us do figure 2 on the next slide. Okay, but let's do it on the next slide and understand what's happening here. Okay, so you have that. Okay, here is the slinky spring, and somebody's holding it there with their hands, and somebody's holding it with their hands there like this. And now they're moving it up, tossing it up, and suddenly, I mean, it was tossed up here, and these pulses started migrating towards each other. And what you then can see here is something similar. Something similar.
They combined.
Yes, now they're combined now to form one big pulse. Okay, good. They combined now to form one big pulse. And so this one now, I want us to call this one figure 2. So in figure 2 now, the two pulses now we had, so one using a spring used both hands to lift the spring up, and then the pulses were formed. And then now suddenly they started to migrate towards each other. So they combined to form one big pulse. Okay, you can see one big pulse. So now figure 2, let's discuss, let's elaborate what is happening here in figure 2. Where the two pulses cross the disturbance. The disturbance increases. So where the two pulses cross, the disturbance increases. Now you can see that the disturbance is big now because the two pulses crossed, they met, and therefore the disturbance increases. But also superposition leads to constructive interference. So we describe what we call superposition. Superposition leads to constructive interference. Okay, so now figure 2, where the two pulses cross, now when they combine, they form a big disturbance, so the disturbance increases. Now superposition leads to constructive interference. Okay, so you continue. Constructive interference. Now let's look at the next one. Figure 3. Right after crossing, the two pulses carry on. They carry on unchanged. So now you have the slinky. Okay, so sort of clearer. Okay. So now they combined. So after they combined, then this one still continues in that direction, and this one continues still in that direction, but you still have the hands here, like this. And so this one continues that way, and this one continues that way. They combined, but still now they move in the opposite directions now, towards the hand. So after crossing, the two pulses carry on unchanged. Superposition. Superposition. Okay, so now the couple of things that Okay, learning superposition, I want us to focus on the principle itself, called the principle of superposition. Where pulses cross the combined disturbance at any point is equal to the sum of the disturbances. So now we continue. Okay, we are focusing on the principle of superposition, where two pulses, right, where two pulses cross, the combined disturbance at any point is equal to the sum of the disturbances. So this is what we have, where pulses cross, the combined disturbance at any point is equal to the sum of the disturbances. So we saw that is the sum of this. So the principle of superposition says where pulses cross, the combined disturbance is the sum of the disturbances. So we are saying what is happening is that the pulses cross. When the pulses cross, there is a combined disturbance which is equal to the sum of the disturbances. The sum of the disturbances. So we saw that here the pulses crossed. It was a smaller pulse and a smaller pulse. They crossed, and then whenever they cross, then the disturbance at any point is equal to the sum of the disturbance. So the disturbance here sort of increased in this case. So, but need to understand that there are two types of interference. So there's either constructive interference or destructive interference. So let's talk about this. Let's talk about this. Constructive interference. Right, constructive interference. Right, constructive interference. We say that constructive interference takes place when the disturbance when the disturbance Right. Takes place when the disturbance of the combined pulses is greater than the individual. Okay, just 1 minute. Hello? Yeah, fine, thanks, and you? Oh, okay, I'm coming now. Okay, give me like 2 minutes, I'm coming, okay? 2 minutes, Leander, okay? You still with me, Leander?
Yeah.
Okay, I'm coming in 2 minutes, 2 minutes.
Yeah.
Leander.
Yeah.
Here, Leander.
Yeah.
Okay, I'm so sorry. I just had to speak to somebody at the door. Somebody had parked a car and They were here to deliver my goods. Okay, now I was saying that constructive interference takes place when the disturbance of the combined process is greater than the individual rights, individual disturbances. Okay, so this refers to constructive interference. Takes place when the disturbance of the combined processes, when they are combined, you have that the disturbance is greater than the individual disturbances. So here you had the individual disturbances and those were small, but now when they are combined, the disturbance was big combined. Okay, so this is called constructive interference, and then there's something that is called destructive interference. Destructive interference. Destructive interference. Right, we say that destructive interference right. Destructive interference takes place when the combined disturbance is smaller than the individual disturbances. Right, so those are the kinds of things. So now, right, let us see what we need to do now. An example. Let's have an example. Right, in this example, we're effectively saying calculate. What time is your next class?
I don't have classes anymore.
Okay, that's awesome. Yeah, I'm just finishing this, okay? I know that I'm going a little bit after a couple of because I ran out, so I'm gonna like go beyond by like 2 minutes. I'm not gonna take too long, okay? Right. I want us to discuss some calculations, like calculate the amplitude of the combined pulses in the figure below. Okay, so you have that, this one. There is a pulse here like this. And then it goes up. And then Okay, so like that. And then now you would have the other one when they're combined. And then now you still have the hands here. Still have the hand here, and you have the hand here. Right, like that. And then now this one here is the okay, this one is 100, it's plus 120 millimeters. So we have here we continue. And then here is 80. Okay, right. Okay, 80, and then now the question is, what would the combined one be? Let's look at the solution to this one. Let's look at the combined one. Solution. Right, so obviously looking at the solution now, you can be able to find the combined parts here. And so what is the answer to this? The amplitudes.
It's 200 millimeters.
What do you think is going to be?
200.
Good, well done, well done, well done. Excellent, you are right. So the amplitudes of the pulses right are plus 120 millimeters and plus 80 millimeters respectively. And so using the principle of superposition, the combined amplitude combined all right, so the combined amplitude is equal to plus 120 millimeters plus, and you plus 80 millimeters, and if you add them up, you get plus 200 millimeters, which is 200 above the rest position. So I want to give another example, the last one. The last example for today. Okay, so here now you have this one. It's a small pulse. And it goes straight. Okay, so we continue. So it goes up like this, and then here, this one is going down like this. So now so you have now this one here. Here's the hand. Here's the hand. So now this one is the hand. This one is a spring, but now it's moving this way. So this one is going the other way. So right, so this one goes up here, plus 120 millimeters. And this one, okay, this is our last example, please. I'm not going to keep you very long. Okay, so now here is the spring. And then now, okay, you give this spring a push up with one hand, and with the other hand, you sort of give it a push down. And then we understand, therefore, that it's going to continue moving in the directions that I've shown in blue. And so the hands are holding it at both ends. But now we can see that what we can see as the outcome is like this. Here is the spring. So it's just showing some pulse here. But now, as it's showing this pulse, what you can see is going a little bit up, like this. Okay. Now, here comes the question. Calculate. So last example, calculate the amplitude. The amplitude of the combined pulses in the figure. Right. Oh. Right, let's look at the solution now. What is the solution? So the combined powers, or rather the combined amplitude, is, okay, so here it is going to be the plus 120.
Is it 40?
Well done, it's 40. And then this other one is negative. Well done, it is 40. Our last example, just 40 millimeters. So it's 40 millimeters above the rest position. Above the rest position. So it's going to be, the combined one is going to be 40 because we're just adding them up. Okay. So yeah, I must thank you for joining us today. And I spoke to your mom that we need more time before Monday so that we can practice more. So your mom is going to let you know, but yeah, we need more time to practice more so that you can like master everything and like excel on Monday. So yeah, your mom is going to discuss, we're going to discuss the time and see what time is the best so that we can like practice more and more. Okay.
Yeah.
All right. So that you can get like 100% because that's what we want. So, but for you to get 100% on Monday, we need to like practice more and more. You must learn more tricks. You must learn the tricks. You must master the tricks. You must master the different challenges and the tricks that come with the questions. But some of the questions are tricky. You know, you look at the question and it's tricky. You wonder how to start, how to do it, what the correct answer is. Those are the kinds of things we're going to discuss. Okay, thanks a lot, Luyanda. And I'm going to send the links to your mom to these videos so that you can like watch them when you want to watch, etc. Okay.
Yeah.
All right. Thanks a lot. See you next time. Your mom is going to let you know. Okay.
Thank you.
Thanks, Luyanda. Goodbye, Luyanda.
Bye.
Bye.